Okay, number three. This one was a tricky one for a good chunk of you, and I understand it was a tough one. There are several things in here that take you out of your comfort zone, and you really have to try to work on getting comfortable in these areas. But I understand. We have a ball getting whirled around in vertical circular motion. We are given the mass in terms of variables. So we know it's mass m, length L. Um, at the top of the circular path, the tension of the string is twice the weight of the ball. Tension in the string is twice the weight of the ball. That was important information. The bottom, the ball just clears the ground. Basically, that means the circle itself is on the ground. Air resistance is negligible. And another key thing that we really had to catch, express all answers in terms of M, L, and G. And this is the spot that you have to get used to. It's very common for problems in AP to be in letter form. One way to try to remember to do that is to make a proper knowns list, which is a theme of Muso, and I understand it might start to irritate you, but it's true. Make a knowns list. So A, complete the force diagram of the ball when it's at the top of this path. A lot he did fine here. I can't complain too much. But let's grab that knowns list. If you write this down, even though you don't have numbers, M equals big M, R equals big L, A equals G, M, L, and G. T, which I'm referring to as tension, is 2mg. Because remember, it said tension is twice the weight. We can either represent weight as W or F sub G or mg. And since it says it's twice the weight, we gotta multiply by 2. A lot of you forgot that weight is both m times gravity. I saw multiple just m, and I saw multiple just g. It's both mass times acceleration due to gravity. Don't forget. So here's my knowns list. At this point in time, I can only use this side. I can't have a T in there or an A or an R because that's not what it told me to do. All right, complete the force diagram. To get, this was 2 points. To get both points, I needed to successfully draw both arrows. The tension was twice as long as the weight, but it did not need to be. I did not deduct a point if it was equal in size or smaller. You lost points for any extra force you gave. There were normal forces in here. Nope, that's not true. There is no normal force. Some of you had arrows one way or the other, left or right, and I presume you were trying to indicate the direction of its velocity, but nope, there's no force there. I even had the occasional tension drawn incorrectly. The tension was out over here instead of here. This is fundamental centripetal force. No matter how difficult the problem got from here, you have to be able to do this. Study it, review it. Remember, the string is pulling it in, and the weight is pulling it down at that spot. And that was A. I'm going to move this out of the way so I can talk about part B. Now, B says determine the magnitude and direction of the net force in the ball when it is at the top. This was relatively difficult to understand what it's asking for, simply because you may have made a fatal mistake of assuming that meant just simply write net force equals ma. This was the right answer. Ignore this. This was from a previous part. This is how to successfully do part B. Let me walk you through why this is the only right answer, and then I'll try to talk about some of the common errors. So we know the net force has to be centripetal. It is moving around in a circle. It's very clear it's a circular motion problem. In this case, the net force is mv squared over r. Now, of course, we can say the centripetal force is MA, but we have to be specific that that A is MAC, centripetal. And don't forget, A sub C equals V squared over R. So we're using the version of the equation that is mv squared over r. But that's not indicating what the forces are. It's not the magnitude and the direction of the net force. That's indicating that we know the net force has to be centripetal. So this is the requirements in which the net force needs to fulfill. Really, the net force came from the true forces at play here, which is tension and weight. Recognize that both are down, so some of you may have unintentionally indicated them as a negative, but you need to realize, again, we're going to treat center seeking as positive. So in this example, down ended up being positive. And so I first let off by writing T plus mg, just so I can remember that I know that this is my tension and weight. Then I took this entire equation, took it out of equation form, and put it into variable form. So I replaced the m with big M. I replaced R with big L. I know R is L, it's string length away from the center. Replaced T with 2mg. And replaced little mg with big mg. Turns out that just adds right up to 3mg. So this first part right here, this wasn't necessary yet, but it helped for the future part. 1 second, I gotta tend to my son. Okay, I think he's good for now, but I might have to pause it again, so bear with me, kids. Here we go, part C. C simply want to know the speed of the ball at the top. So I want to know what its velocity would have been when it was up here. Remember, this isn't a force, it's velocity. What is that speed? Well, we knew that V is inside this version of the equation. So once again, MAC could have been used up here, but you really had to make sure you remember that centripetal acceleration included velocity in it. So if you didn't remember that A sub C is V squared over R, I can see it being tough to get to that next step to solve for V. And so where did this come from? I simply rearranged this equation for V. Let me rewrite it and I'll show the rearranging for you. I have the original equation is, let me grab my marker here. My original equation is mv squared over L equaling 3mg. I'm trying to get V by itself. I see that the m's can cancel out. I'm going to multiply both sides by L, and then I'm going to take the square root. So I get V is the square root of 3gl. Again, notice I'm leaving it in terms of L, not R. Now, you likely only lost 1 point if you failed to indicate this as L instead of R. And you would have lost that point earlier on. So if you had carried R over throughout the whole time down to this stage, you wouldn't have lost the point again. Now, if you end up using the R in an incorrect manner later on, you might lose another point. But for now, you did not lose any additional points. So that's, again, how we got to that velocity value. I'm sorry, I was trying to get the point breakdown, but I honestly don't remember completely the exact breakdown. I want to say B was worth 3 points and C was worth 2 points. But I could be wrong there. It could have been 4 and 2. I guess we'll see at the end once I add it all up if I think to. Okay, time for part D. Part D is interesting. Ends up being a hidden projectile motion problem within this, which AP likes to do. So stuff never really goes away. Keep that in mind. So we want to determine, first of all, when it's at the top of its path, the string is cut. And part D wants us to figure out how long it takes to hit the ground. So up here, it's traveling this way, the string gets cut, and that ball ends up traveling in a projectile manner. What you gotta really pay attention to is that ball is moving in a horizontal dimension in the beginning. So let me clean this up, and let's take a look at the work. Actually, I'm going to redraw. I'm going to redraw the circle real quick. Actually, no. We're going to look at the ball at the top, and we're going to see that it has motion. That initial velocity is now traveling to the left. We want to figure out time it takes to hit the ground. So let's take a look at what we know, what we've got. Now, in the vertical sense, the object has no initial velocity. This is only in the x dimension horizontally. In the y dimension, the initial velocity is 0. It's going to allow us to calculate time, because gravity, which is pulling it down, only affects that y dimension. First, the change in distance. It's going to be 2L, not L. The problem tells us, or not the problem, but we see that the radius is L, and when we're at the top of our path, we're going to be 2L up, one radius, and then another radius, so a total of 2L. The acceleration is gravity, and we're looking for time. From this, we see we use this equation here. Initial velocity cancels out. I rearrange this for time, plugged in 2L and G, respectively, and we get either of these two answers are fine. You could have left the 4 under the radical, it would have been perfectly fine. Or you could have recognized that that's actually going to be 2 times the radical L over G. That's it. That's the time it takes to land. We're going to need to probably use this for part E, so let's keep this out. And we're looking at part E. We want to know how far forward it actually travels. Now we want to know that horizontal range. So we're looking at x dimension, or horizontal dimension here. And so, taking a look at the work. Let me jot down a knowns list to go with this. We know, or I'm not jot down, point out, we know that the initial horizontal velocity is what we had determined earlier in part C. That is the velocity that we're using here. We now know the time it takes to fall. We got that from part D. And we're looking for that x dimension, x displacement. We're looking at the average velocity equation, plugging in. You need to remember that when you multiply radicals, you multiply inside the radical and the outside terms respectively. So the 2 stays outside. We're multiplying radical 3LG times radical LG, which turns into radical 3L squared. The g's end up canceling each other out. And this here is the range. Notice once again, I kind of threw out that we kept it in terms of the variables given. So, L is like the number, but instead it's the variable. All right, and that is the end here. The point breakdown, we're at 5, 6, 7. I believe each of these were worth 4 points. There you go.